Hello, is it audible? Hello, is it audible? Hello, Bharat sir. Is it audible? Hello, Bharat sir. Bharat sir, is it audible?
Yes, sir. It's audible.
Okay. Hello. Good morning, Shubhankar sir.
Yeah, good morning, sir.
Now you are presenter. You can share your slide.
Okay. Can you see the screen? Hello.
Yeah, it's sharing. Yeah. Yeah. Is it? It is visible now.
Yeah. So, how many candidates are there for joining this?
Around 100 participants. 100. But
So,
only few are joined. Yeah. We'll wait
okay.
for 5 minutes more. Okay.
Hello, sir. Dr. Chittakan, sir.
Yes. Yes.
Hello.
Please.
Yeah. The time period is scheduled for 2 hours.
2 hours. 10 to 12. Okay.
10 to 12. Okay. So, firstly, I will brief about the layout design and challenges. And
Okay.
then I will show that how to prepare a layout. So
Okay.
two
Okay.
hours is very less time. So for showing everything, like whatever I will tell, like DRC, LBS, RCX,
Ah.
ECX, those things need time.
Okay. Okay. So take it up to 12. Then if any another time slot, whatever you want to cover, you cover. Right.
Okay, okay, okay.
Any other
Not
time
a,
slot.
no, actually, 2 hours continuous after that it's difficult.
Yeah, yeah, yeah. After 2 hours, it is difficult.
So
So you can take your slide up to around 40, 45 minutes and then you can start, right?
yeah, yeah. It means I will try my level best, but
Mm.
I just show that whatever the layouts are there, whatever the challenges are there, what are the short keys of layout design.
Okay.
The attendees have the cadence in their
No, no, no,
institutes.
no, no. They don't have their training.
Oh, 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 oh. Then
But most participants are from MTech and PhD and BTech also. Some are BTech, but they are maybe familiar of this layout design. So
okay, so I think that the technology file and DRC about those only a
yes,
talk is good enough for them because they don't have cadence in their institute, so it will
yeah.
be difficult. Every tool has different technology files.
But you can show what are the
Yeah, yeah, yeah.
features available. Okay.
Features available and how the from schematic to symbol to layout.
Yeah, yeah.
Yeah, that can be some expectation.
Okay. So we'll wait for 2, 3 minutes more, then we'll start. Okay.
Yeah. इवेंट सोच लो जब से वो स्टार्ट है तब से हम लोग को ऑन रहना ही पड़ेगा तब से तीन बजे था ना तो 3 बजे से हम लोग को ऑन रहना ही पड़ेगा पूरा इवेंट मतलब ये एज ए न्यू स्टूडेंट है उनको
So
उनका
I think
थोड़ा
time is 10
बताना पड़ेगा
o'clock
कि क्या क्या
now.
प्रोसेस है
Shubhankar sir, are you here? Hello, are you here, sir?
yes sir yes sir yes sir
So we can start now. I think it's 10 o'clock now. Okay.
yeah
So around 37, 38 participants joined. So later in 5 minutes, they might be joining. Okay. So,
okay
so welcome to third day of the workshop on emerging CMOS technologies and beyond, trends and challenges. So today we have scheduled three lectures. Okay. First lecturing session one by Dr. Shubhankar Majumdar. He is assistant professor in Department of Electronics and Communication Engineering, National Institute of Technology, Meghalaya. So he is a assistant professor there, and he's, he has done his PhD from IIT Kharagpur. So he has a very good experience in the field of VLSI design, CMOS design and challenges, and his research area includes low power as well as high power semiconductor devices. So I welcome Dr. Shubhankar for this talk on the layout design and challenges. So this talk will be a mix of theory as well as practical. So first few minutes he will going to discuss about the layout design and challenges, and then he will demonstrate through Cadence tool about the features, how to design a good layout using Cadence tool. And Cadence is considered to be a industry in the standard tool. And if the participant get acquainted in this kind of tool, so there will be a future opportunities in terms of job perspective, in especially in VLSI design companies. Okay. So welcome again, sir. It's over to you now.
yeah thank you sir thank you Dr. Chetakant sir for the introduction so today's topic is layout design and challenges so we will be focusing on whatever the designs issues are coming and the challenges issues are coming in the layout perspective those will be reflected in today's talk so in a layout, before going for a layout, we need some kind of schematic. So our today's outline of my discussion will be focusing on CMOS layout design flow. Then we will discuss about the CMOS layout design rules. Then the technology files. What are the technology files? Why they are essential for layout purpose? And then what are the command file formats? For DRC, ERC, and layout versus schematic. ERC means electrical rule check, DRC means design rule check, and layout versus schematic means whatever the schematic you have prepared based on that, on the layouts are representing or not. So these are the essential things which we will be looking on today's talk. So after this talk, I will be showing a demonstration on Cadence tool. Vertiso. Cadence is a company name. Tool name is Vertiso. So on Vertiso, I will be showing the schematic, and after in the schematic design I will be demonstrating it on a layout via symbol. Means this is the basic theme that first you have to draw a schematic, then you have to analyze the schematic design in the spectra, and after that you have to make a symbol of the schematic, and then that symbol, from that symbol you have to generate a layout. You can directly generate a layout also when your fabrication lab is there. Means your own fabrication lab is there, your own technology files are there, these all are written. Means the technology file and command files, these all are given inside the process development kit. So Foundry provides the process development kits. So the flow is like Foundry provide a designer a PDK, which is a process development kit, and that PDK, from that PDK they are designing a circuit, and that circuit is utilized by giving to the tape out. Means in layout we have to go to the tape out, and after tape out you can send that tape out to the foundry, and then foundry will fabricate it, and after that foundry will return the ICs. So this is the workflow. So layout is also important, because from layout perspective only we will able to get to know about the parasitics. Means various types of parasitics are there, like line parasitics are there, then metals are parasitics are there, then well parasitics are there. So these parasitics are nothing but a resistance, capacitance, inductance lumped loop. So these parasitics are generated while we are fabricating. So representing a schematic, simple schematic simulation can work ideally. But when we are changing the environment from Spectre to Assura, then the output in the post layout simulation will be good. Means we will be including the parasitic effects of that type of foundry PDK, whichever you are using, TSMC, UMC. Now in India also the chip fabrication is going on. So the ISRO SCL is providing the Semiconductor Corporation Limited of ISRO is providing their own 180 nanometer technology files. Means those are the PDKs of the SCL. SCL PDKs are there. So you can contact them. They will give their specification. If you are able to design on those specifications, then that chip can be fabricated. So now this is the design flow. Means first we have to determine the system specification, then behavior design, then structure design, then P&R, means power reductions, those we will determine. Then we will see the layout verification. And in today's talk I am only focusing on the layout verification. Means the DRC, LVS, ERC, these rule checks and design rules we will be talking about. Then after design layout verification, we are going for a post simulation, and that after post simulation, you are sending the tape out to the manufacturing or the foundry for manufacturing. After the silicon over the CMOS manufacturing is done, a packaging is done, and different type of packaging are there. SMD packaging is there, DIP packaging is there, different type of packaging is there. After that, we will test the IC. So this is the flow, design flow of any kind of IC fabrication. So this design flow is always opted whenever we are designing any IC. Now, so we are only focusing on layout verification. So now first is rules in one layer. Means caused by manufacturing limits. Various types of manufacturing limits are there. As you know that various types of manufacturing processes are there. One is lithography, second one is doping, the third one is etching, fourth one is your patterning. So these all are like passivations, though these all are producing some limits, because in real time everything has some limits. So these all are producing some limits. So those limits are incorporated in the technology file which is supplied by the foundry. So without that technology file, without that rule sets, technology rule sets, you cannot design a IC. So those rule sets and technology files are supplied by the foundry itself, and basically those all are utilizing the lambda rule, inside. So lambda rule sets are used. Now the rules of spacing, width, notch between same net, like these all are the basic things which are incorporated in the technology file. Like you cannot create a notch, triangular notch, because of the limitation of the lithography etching. So you cannot design a triangular notch. You have to design everything as symmetry as possible. So in layout, everything is in symmetry. Means the upper side is lower side. Means a symmetric pattern should be maintained. So now some structures have rules that is must have exactly fixed size. Means you cannot see like a big width transistor. So for larger width, they are utilizing fingering technique. So this fingering technique involves various types of repetition of the same fingers. So the symmetry of the design will be stabilized. So a larger structure is distributed into smaller fingers. So for the symmetry of the layout. Without symmetry, you cannot fabricate that thing. Means basically the tape out which we are sending to the foundry is the only containing the mask level lines, means which mask, which lines are in which mask. So different type of layer, different type of mask. So if you are reducing the layers, you are reducing the cost of the mask, and each mask costs about $5,000. So based on that, reducing the layers, reducing the cost. So, but due to some issues like interconnections and all, you have to have increased the layers. So in tape out, the information of the layers are there. Means tape out is generally is in the format of GDS2 pattern. So GDS2 file you are sending to the vendors. That GDS2 file is only containing the mask information, that which on which mask, which line is there, which mask, which process you have to adopt. Means you have to make a pattern, or you have to make some diffusion, or you have to make some oxidation on some patterns. So those are there in the GDS2 file. So rules in one layer wide structure, means if a wide structure is there, as I have told earlier, that layout should be symmetric in nature. So spacing rules often apply for larger wide structure. For instance, gate is spacing for gates less than L minimum is different. Metal spacing of for wider metals can be different. Via overlaps can be moved for wide metals. Then how to find a wide metal? Can we use a geometric function for expand, shrink, etc.? Yes, we are in layout design, we are utilizing geometric optimization. Those geometric optimizations looks on the symmetry of the pattern, and then there are also looks on the technology file. Means based on the technology file, the minimum and maximum, they are looking on the layout size also. So those optimization you can easily do in any kind of tools. The freeware tool for layout design is Magic. Magic VLSI, then APDK is there, Glade and Magic VLSI, these are the free tools which are freely available. So you can utilize and you can see that how the hello, is I audible? Hello.
Yes, yes, you are audible, sir. Continue.
Okay, no, Shubham Jain was telling some echoes are coming. So, yeah, so now those are in the free software also. So you can utilize those free software, Magic VLSI and Glade. So these two are also utilizing a process optimization technique, means geometric optimization is going on, the mathematical expressions of geometric optimization is running on inside the layout design, and they are checking that the minimum and the maximum of the layouts, means in the line is minimum or maximum. Based on those optimization technique only, the DRC rule check works, means the design rule check works, that this is minimum or this is maximum. This has been evaluated. Means if a transistor level circuit, if you are seeing a IC, it's having about a billion of transistors. The new Intel i7 is there. So those are there. Means optimization techniques has to be utilized. So those are utilized. Now rules are in one layer like a slot. There are also maximum rules like manufacturing of large continuous region can lead to the stress and cracks. So for this reason, we are not going for a larger area deposition. Like if you are doing a metallization through RF sputtering or a evaporation, evaporation gives the less porous area. So and the if the metal is less porous, then the probability of electron migration will happen. So for this reason, we are always focusing on the RF sputtering, DC and RF sputtering. If the material melting point is high, so RF sputtering. If material melting point is low, then we are going for a DC sputtering. So RF and DC sputtering is used for making a large continuous area region. So those also having some issues like roughness. Through AFM, you are seeing the roughness of the surface. Those are the issues. Now, for those issues only, we are make a layout in the symmetric way. Means one symmetry is second symmetry. We can overlap one symmetry over the another. So those type of architecture we are using. Now, the symmetry like no square can be excess than 10 to the 10 cross 10 micrometer square metal line. So we have to have decrease our metal line from this type of area. So now wide metal line must be slotted. If a wide metal line is there, some holes you have to be give to flow the electro, means to flow the heat, means why the electrothermal electro mitigation happens, because the heat produced due to the large current on the metal, then it result to the due to the heat, the cracks develop. As you are knowing that heat is equal to H is equal to I square RT. So if I is increasing, means the current is increasing, then the heat will increase, and if the heat is increasing, then the electromigration happens or a crack happens in the metal lens. So now this can be used by simple chopping some area. So these holes give makes big for making a heat sink kind of structure. Means whatever the heat is developed, those will be extract out from this hole. These are the basics of the thermal management. For thermal management of the metals, we are utilizing these type of chopped slots. Now, if in your layout also a thick metal, a wider metal is used, so in that you have to have put your slots. Now these slots are utilized for thermal management. Now rules between the layers. Different type of layers are there. Now alignment is a issue. And alignment is the basic thing for lithography. in lithography process, you have to have put a alignment mark, not only one. If after every blocks or every device, you have to put a alignment mark. So this makes the precision more accurate. So your accuracy of your layout should be very, very high, so that whatever the alignment is there of each device or each circuit should be proper. If it is not proper, then a mismatch will happen like this. Then it will be ideally short or ideally open. The circuit will be ideally short or ideally open. So for this reason, there is a issue, or the extension will be causing extra parasitic effects. So whatever is expected, you cannot get those output. So enclosure and overlap is a issue. And one more thing I want to tell, that in this type of enclosure or overlap, you have to have make one isolation line after every annual. Some isolation lines should be there. So those isolation lines are helping you to make or to see whatever the changes is happening is not affecting your adjacent devices. So isolation is always required in any kind of devices. Now, this is the, before this is the top view. Mask, always remember that mask is the top view of your circuit. Now, this is the cross-sectional view, means in your CMOS technology, what is happening, means after which what is happening, means first consider contacts of drain and source. Now ideal minimal n plus size is there, silicon oxide is there, aluminum metal lines is there, then a contact is there. This contact is different with the metal contact. So because polysilicon is always different with the metals, but we are putting polysilicon and a metal and one contact when we are designing a circuit in a layout. Then if it is misaligned, this, like if it is misaligned, then what will happen? The short circuit between the drain and source substrate will be happen. The solution is contact hole must be smaller than the active. So whenever you are designing a layout, you can see that contact is always smaller than your well or than your active region. So this is the basic theme which can overcome your overlap issues. Now, these wires, these metal contacts, these wires means if two layers are there, one drill and then putting the wires, metals, those are known as wires. These are also utilized in the PCB design also. In PCB design, what we are sending? We are sending a Gerber file. And in IC design, we are sending a GDS2 file to the foundry. So PCB design, if you know the PCB design, it will be very easy to know or correlate the IC design. So in PCB design, we are sending the Gerber file. We are putting some wires for thermal management. So those type of wires we are putting here also. So metal between the two metal interconnections we are basically putting. If a four layer PCB is there, then what we are putting? Top layer is VDD, means power supply, and bottom layer is ground. Then we are putting a wires, or we one more strategy which is more efficient for PCB design, that design you are making at top surface, at bottom surface, and at the between those two bottom surface, two layers are for VDD and for ground. So every interconnections are going from circuit 1 to the VDD through wire or ground through wire, and likewise from circuit 2 also or circuit plane 2 also to VDD or a ground. So the same logic comes here also, means metal line 1 and metal line 2 interconnections are put in by wires. So this is also accurate because some kind of interconnection will be there. Wires are always used for two things. One is interconnection, another one is your thermal management. So these are the basic things which you have to remember before these rules for contact can be aggressive and complicated. Metal must extend via on at least two opposite sides. This is often allowed, like we can put the metal wires in between the two lines, and this is not used because wires cannot be put at the extent of any exterior points. Now, butted contacts. We are utilizing the butted contacts because this, if ground is like this, then the area of the metal line of the ground is increased. And you all know that resistance is equal to R is equal to rho L by A. So if the area is increasing, the resistance is dropping, but the issue is that the length is also increasing. Means here the length is increasing. Area is increasing, but the length is also increasing. So we are utilizing the butted contacts for the ground. So if the ground is small, we always remember two things, that VDD line and ground line are always top metal line, means like M9 or M12, because for easy means lower resistance value, we are going for a larger area metal lines for lower the resistance. So those are utilized for ground and VDD. So we often need a P plus substrate contact loose to N plus contact, whatever we are utilizing, that source and substrate body contact we are giving. Now for body contact, it is a issue. When body and source are connected each other, we can collide those two and utilize the circuit. Now, this is the basic thing, that area fills are always utilized. Like we are utilizing some areas, like some vacant areas are there. So those vacant, you cannot put like simply a vacant area in a chip. You have to fill every vacant area. So those vacant areas are filled by the top metals, which is low resistive metals. Those low resistive metals are utilized to fill the areas. Now, the total covered, it is just a case study, that the total covered area on most layers must be within a certain limit, like zero point 0.3 to 0.8. This guarantees homogeneous production. Means it should be a homogeneous and a symmetry production. This rule can be local or global. That is, it must be fulfilled each area in 100 cross 100 micrometer, shifted by 50 micrometer in X and Y direction. If the design has too few structures, extra structure must be filled in. This can be done by scripting. Simple scriptings are there. So to avoid photodiodes, means if there is no metal lines or some vacant space are there, those will be like acting as a photodiode. So no fill area should be not present. Now some process steps can deposit. It's a case study for an antenna. as we are going for a RFIC design or a mimic design, those antenna and whole circuits are integrated inside a chip. So those are like some process steps can deposit static charge on structures, like you are doing some passivation or oxidation. The oxygen ions are getting and making a charged area, charged surface. So those charge means the charge Q leads to the voltage and destroy the transistor gates. So these parasitic charge or a fixed charge or a trap charge, these are more decremental effects on the transistor. So most dangerous for large circuit where the large Q is there, means large charge are trapped and small gates are there. So small capacitance, large gate charge, what will happen? Large voltage will be developed, and that voltage will be showing a decremental effect on the whole circuit. The ratio is calculated for each gate. If it exceeds a value, there is a danger for an antenna error. Now, antenna errors are eliminated. A drain of a MOS is connected directly. The drain diode has enough leakage to discharge the gate. Often the driver is connected to high metal lines and is not seen in the early processes. Now, the explicit issue of these type of things can be addressed by utilizing a high metal lines. So, higher the metal lines, lower the resistance, lower the impact of the charge deposited, and after every processes, it is recommended that one passivation process is should be put to decrease the charges. So now it is a case study that one antenna is there. As you are all know that any kind of line which is lambda by 4, that can serve as a antenna. So any radiating substance is act as an antenna. It's not a big issue to create an antenna inside a CMOS. Only the length of the area will increase. So if the length of area is increased, then the trap charges is also increased. Then the issues with the metal lines comes, of course. Then antenna and gate is connected. Then what is the issue? This is the protection driver diode should be put. If a protection diode is put between the N well, N plus well and P well, then there is no issues with that. Whatever the voltage will be there, that voltage cannot be go beyond that diode. So now some more metals are there, then some tie downs should be required. Means whatever the metals, if they are connected to the antenna, then a bridge type structure should be utilized. This type of structure should be utilized. Now, some hot wells, now the wells become very hot, and those wells should not be merged with each other. Now, if you are merging the two wells, then there will be a short kind of thing, because due to the thermal leakage, means due to the higher temperature, the thermal leakage will happen inside the silicon, and then the charges will directly connected with each other. So the two wells become connected or shorted. So sometimes annuals are only different potential, and these are affected in the source follower type of design. Now such wells are called hot wells. There are sometimes symbolic layers to tell the tool explicitly that the well is hot, and that is more severe rules than we are applied. Now the issue is Now we come to the technology files. Means what is the technology file? How these technology files are utilized? The technology files are providing some kind of information. It adapts the CAT to. It shows different layers through different type of colors. Now the menus and commands, those are shown in this, and from there we are specifying some width and spacing, provide some parametric cells, P cells, which are previously they are designed, means the foundry has designed the internal circuit of a P cells, of a MOSFET or a cap. So those are pre-defined cells are present. So I will show that what are the parameterized cells and what are the how these layers are shown in the CAD tool, Cadence vertical tool. Now then, what are the menus? How you can make a contact? How you can make a wire between the two things? How you can join those things? And then we will discuss about the simple DRC rule check, ERC rule check, LVS, layout versus schematic, and after that the two comes in the post layout simulation. What is layout parasitic extraction and another is parasitic resistance extraction. These operations are guided by command file. Command file must be consistent with process. The content of command file specify source data information, process rules for verification, device parameters. These are the content which a command file shows. Now, we will be discussing about the structure of a command file. Now, description block is there, input layer block is there, and operation block is there. In description block, there will be, it defines the database name, format, and IO information, input output information. Then in input layer block, this is a layer number block, define input layers and connections. Then operation block, define layer operation and verification type. These all blocks are interrelated and is written in a single file. That file is known as command file. Now, in electrical rule check and design rule check, two things are there. So electrical rule check is always saying that electrically a metal line is floating or not. Antenna rules are taken in consideration or not. Then drain and source of the MOSFET is shorted or not. Every electrical kind of things are considered in electrical rule check. But on the other hand, in DRC, it is only seeing the DRC rule check, means lambda rules is followed or not. Whatever the lambda rules provided by the foundry in the technology file, those are taken care or not. So this is the basic difference between the DRC and ERC. In ERC only they are looking on the electrical rules, that anything is shorted or anything is opened or anything is floating. Those types of rules are determined in the ERC. But the distance between two polylines or two metal lines are less or what, those are not considered in the ERC. Those are considered in the DRC. For this reason, this type of rule check is known as design rule check. Yeah. Now in DRC, prepare a layout database, which is a tip out. You can easily create a tip out. Then run Dracula command. One command is there, command window is there for file interpreter, and then start a DRC. So now this kind of interface comes when we are seeing a Cadence tool. Now, for a different type of levels, they will be showing some warnings like NMOS body connect to ground. It is required PMOS body connect to VDD. These are the basic things. This will show in the schematic. Now layout and schematic, same WIL corresponding to MOS. These all will be determined. Now prepare DRC command file. In a DRC command file, description is there. Under that description, top module, consider the cell name. Then file name of the layout database is there. Then output name, output debug file name is there. Then you print the DRC. And these all are same in your licensed version or in your freeware. The steps will be same. So whatever tool you are utilizing, you can see those all tools. Means these type of things will come in those tools. Yeah. So the reading of how to read, some if some errors are there, those will be highlighted, and the positions of that errors will also be highlighted. The DRC runs whenever the no error comes and everything becomes 0, 0, 0, 0. So the window looks like this, means whatever the error are there, they are showing here. If no error is there, they will show no error DRC clean. So now some what LBS does: extract schematic netlist, travel down the hierarchy until a view is in the stop list. For instance, we can view an inverter as a cell not resolved into MOS, then ignore the symbol. For instance, now the analog library which is consisting in the Cadence is only for utilizing schematic, not for your this layout. So we remove everything of analog library like VDC, VDD, those ground, those contacts are removed by a pin. So because analog library files are not situated inside the layout, because it is not a technology parameter, it is only for utilizing the testing of your chip. Analog library is always utilized for the testing of your chip, not for your fabrication purpose. So testing will come after your fabrication packaging, the testing will come. So the analog library component you have to remove, and you have to make a symbol kind of structure. Then after creating a symbol, the device and nets without labels are often have different names. Now you have to determine different type of structure. Means if in your schematic some errors are there, means some errors are there, the same thing should come inside your layout also. If it is not, then the tool will not show the LBS. Now in layout extraction, the extraction must find the device first, then the geometrical parameter of the device like WL, area of drain, perimeter of drain, area of source, perimeter of source. Then likewise these type of geometric parameters should be there. Then the way this is done which influence the result in special cases, like different type of cases are there, like some width is there, first they will measure it, after that some area is there, then some length is there, those will be measured. And every parameter in Cadence is in micrometer or micrometer square. So these all are like 0.5 e to the power 6 is micrometer, not in meter. Okay. So these all are very small size. Now gives correct result for rectangular mouse, but no good value for enclosed mouse. So enclosed, this kind of structure is not utilized, this kind of structure is utilized. Now, this type of schematic you can easily design in any kind of substrate and any kind of open source tool. If you are interested in open source tool, I will share some GitHub links from which you can easily install and easily run your own open tool of your schematic and as well as for your layout. So in your layout, like these kind of layout extracted, they will directly compare that whatever is put in the schematic is put in the layout also. So these type of pins should be there, then the circuit device should be there, then output should be there. So everything should be registered and labeled nicely so that which can be helpful for your design perspective. Now, that single MOS in schematic, multiple MOS in layout. Single MOS is there, but due to the fingering, here is two finger devices there. As you can see that it is a source, it is a gate, it is a drain, and again a source, again a gate. So two device, one device and two device, but device is only one, but we are doing fingering because layout should be symmetric in nature. So we are utilizing fingering technique, but it is a device. So now they will show that there is a error, but here we are put the width of MV is 2 micrometer and the width of M1 is 2 micrometer and the whole width is 4 micrometer. So in this case the layout, it will not show any error of the layout versus schematic. Yeah, because the width is of the both the things means this and this. This is the gate width. So the gate width total is 4 micrometer, which is satisfying the schematic. So the LVS will show like this. After running the LVS, it will show like this, and then it will show match. But why? Comparison finds parallel MOS with same L and calculates W as W into M. M is the number of fingers. How many fingers are utilized? So now, what permutation of LVS can be done? Now, various types of permutation can be done, like we can increase the width by fingering technique, then increase the length for some cases, then is it okay to swap order of the MOSFET? Yes, it is okay, but the number should be equal. Means whatever the designated symbol is there, like M1 or M2, the same thing should be here in the layout also. Now the LVS flow is like prepare some layout and netlist database DDS2 file, then log LVS is there through Dracula. It is the case of the Cadence. If you are utilizing Cadence 2, you will see the Dracula netlist. Now run the Dracula command and start the LVS. This is the internal flow of a LVS. First it reads the database, top cell name, then expand data from top, extract device and parameters, then it filter unused device, reduce device as specified, then build map of correspondence, then trace from pads, then build device and node maps and comparison and output. So till now what you can see that whatever the schematic or whatever the simulation you have run, those are the minimum things, and the basic large thing is layout design. After layout design only, it can be contacted to the foundry. So whatever the design flow is there, the schematic and the simulation of your schematic is only the 2% of your design part. So after that, you have to design a layout. Then from layout, you have to do the post layout simulation. From that, you have to again optimize your circuit to get a good post layout result. And after that, you are going to make a GDS2 file of the circuit, and you have to send that to the vendor or a foundry. From there, they will send the chips with the package, and then after that you have to test and characterize your circuit. So this is the whole process flow of any kind of circuit design. So now about LVS, the command file, again it is same like DRC. The file, the first line of that will be file name of the layout diagram, then top module cell name, then output debug file name, then output report file name will be there. Then a generated log LVS file for LVS will have HTV, GenPad, then some CDL file, then some cell name, and then exit. So this is the export, how we can export. I will show in your Cadence demonstration how to export a CDL file. So then leading the LVS report, some header will be there, then some layout reduction will be there, then some schematic reduction summary will be there, then some main body LVS report will be there, then LVS repeat summary will be there. Then this is the kind of viewing how you can view the layout versus schematic report. It is a example of a SRAM design. So different type of pads are there, different type of contacts are there. So now after debugging the whole LVS report, the LVS error usually cannot be easily located. Yeah, this is the issue. Then do not verify a block level until all cells within the block pass LVS. Then always clean ERC errors, means nothing should be floated or shorted or opened. So electrical rule check should be cleared before LVS. Then LVS error is usually closely related. That is, one physical error may introduce several LVS errors. So rerun the LVS after fixing an error. So one type of open circuit can produce several types of LVS errors. So LVS result are heavily relied on the correctness of the initial correspondence nodes. That is, the mapping of the nodes between the schematic and the layout must be consistent. So whatever LVS is what? It is the mapping of the schematic and the layout. That mapping should be validate always. So if anything is there, open or short, then you will cause huge number of LVS error. So when LVS mismatch occurs, you always check the specification of input text and map the correspondence nodes. Now, these are the hotkeys which you have to remember for Cadence Vertiso. We will be utilizing these things to simple out our circuit design. So this is my contact. If anyone thinks to contact me, they can easily reach out to me at any time. Hello, Dr. Chittakan sir. Hello. 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 Hello.
Hello.
Yes, sir.
Yeah, yeah.
I have completed my presentation. Now I
Okay.
will show. So let's give 5 minutes to the participants. Then I will start the show. So
Sure, sure. So
okay,
we'll break for 5 minutes. 10:55 है, तो 11 o'clock we'll start the demonstration of layout. Okay.
okay,
Okay.
okay. Okay. Thank you. Message. Where is the message? It is coming. Just one message is coming. Here it is. Hello. Hello.
Yes, yes, you are audible, sir.
Yes, sir. This message from where I can see the message?
Chat box, there are, I think, two questions. Okay.
Yeah, yeah, yeah. I just it blinks that one question has asked. So I am unable to see where that question is there. So
One is asking what is the good book we can refer this, what you told in the lecture.
yeah, Baker book is there. Baker. That is for layout. So
Okay.
it is online available and freely available. And one thing has came that GitHub link. So I have just take the GitHub link. So
Yes,
where
I
I
was seeing GitHub link. You can put in the chat.
yeah, that chat box is not coming. I'm not knowing that. Actually, I am running it in window means Chrome page tab only. Cisco on Cisco, I am not running. Just I'm checking on Cisco.
Provide it later also once
Okay, sir. I will mail you. I will mail you. You can. Then it's okay.
one is asking what is fingering technique.
Yeah, yeah, yeah. Fingering technique is useful when you are increasing any size. So why it is utilized for thermal management, and one more thing is that if you want to address a larger area, means larger width, what will happen? The excessive current will flow because of the area will be increased. So for that reason, the heat will be largely dissipated as a heat is equal to H is equal to I square RT. So if current is increased, so heat will also increase. So to reduce that, we are utilizing fingering technique. Now in fingering, what we are basically doing that we are achieving the same width, but we can achieve that like the width we want to achieve 10 micrometer. Now we can achieve the 10 micrometer width by utilizing 1 micrometer 10 times, and then we are connecting in that 10 times 1 micrometer, that will also behave like a 10 micrometer width. So this type of fingering is used, means 10 finger device is there. So 10 finger device is there. So we can utilize 10 finger device. The number of your source and drain is also reduced. Yeah, for this reason only we are supplying. And I have sent the link in the GitHub link to you, sir. Dr. Chitran, sir. I have sent the link to academy at the rate mnit.ac.in.
Mail. You are
Mail, mail. Yeah, yeah, mail.
okay.
You can share, you can put it in the chat box. Yeah. So I think everyone has came for this session. So thank you for all. So this is the Vertiso 2. Whenever you are opening a Vertiso, it's open like this only. Means first the cadence design system is shown, then whatever the system utilization is there, then the licensing is shown, that whatever the license are there, some warnings, if some warnings are there, they will show those warnings, and then some libraries like Azure libraries where the technology files are situated, those are shown. Now after this, they will show that generic PTK is there. Now, how we can design? We can go here, new library. We can create a simple library. We can create a cell view. So I have created for reducing the time. So I have created the library. So you can create also a library. Like if you are creating a library, if it will open like this. Okay, so whatever library you are creating, so you have to have attached the to a existing technology library. What are the technology libraries? Those are the technology files, or those are the PDKs, process development kits, which are given by the foundry itself. So I have done that. Now again we can go to cell view, means in one folder. It's like library is a folder. Inside that folder, you are going to see the what are the files are there. So cell view is the file. So we can create a file like cell view. This will open like this, and my library name is T1. I have put a library name T1. Now so many libraries are there. Okay, and so many PDKs are also present. So based on that, various types of libraries are there. Then I am using T1. I have created one T1. Inside that, I have created one cell. And first we have to create a schematic. So you can see, you can create, it is a Cadence tool. You can create a spice model, you can create a Verilog A model, you can create a VHDL model, you can use everything. Means in digital and analog both you can utilize. For digital purpose, encounter tool is used for your Cadence, and for digital purpose you are utilizing Spectre. So for digital, it is going from RTL view to the GDS view. Means you are just writing a Verilog code, which you can write here. As you can see, there is an option of this. Yeah. Now we are, as we are showing a semi-custom. It is not a full custom. Digital designs are full custom designs. You don't have to work on them. You have to write a code and pass the codes. They will optimize and they will design your digital ICs. But for analog purpose, you have to go for a analog or a mixed design. You have to go for a semi-custom logic. So here the schematic will be there, then schematic layouts are there. So many options are there in the applications perspective also. So we are going for a schematic layout. Yeah. So this is a file. So I have created this file. Now after creation of this file, a blank will come. I have just delete this all. Yeah, I just delete this all. I will make a new thing. So that contacts are always needed for keyboard shortcuts are always needed. Like if I press I means instance. If I press a instance will come, and I have kept a GPDK, generic PDK for 45 nanometer. So this will come like this, means the symbol is like this. The width of this is 120. Finger width is also 120. If I want to increase the width, I just make it as a 10. If I am making the fingers as a 10, then what will happen? This total width is become 1.2, because it will multiply 10 into finger width. The total width will increase 1.2. So now I will put like this. Yeah. Now I will make a escape button. If I press a escape button, that symbol will go again. Now I want to design a inverter. So I need one PMOS and one NMOS. Now what I can do, again I am pressing a I, then again symbol is there. Now I make the finger as 30. 30 fingers. So 30 finger it become 3.6 micrometer. Now the PMOS is 3.6 micrometer. Okay. Now, okay, sorry. Now this is the issue that it has came NMOS. I want to change this. I press a Q for edit. If I press a Q, I can change the symbol from NMOS to PMOS. Just put a P, it will become a PMOS. See, the arrow has changed. Okay, so this is the basic thing. Means when now these all designs are going upside, so I have to fit in the screen. I will just press a F, it will fit the screen. Now what I can do, I will need a wire, so I will press a W. It will just provide a wire to me so that I can connect every sort of things. So body will be connected to the source. So PMOS and MOS body connected. Now what I will do, I will again press a escape button. So these all sort of things you can come from here. It is a instance. If you are putting an instance, it is a wire. Options are here also, and there is a option of like pin. You can create a pin by pressing a P, or you can click here and it will create a pin. That output is there, output is there. Now this output I will put here. Okay, now as this is very near to this, I will change it. Like it will show like good way that it is showing. Now I will put a press P input. Now input here I am putting the input. Now what I need some wire. Now I need some VDD. I am creating a symbol first, as the VDD interface will be input output kind of. VDD. Okay, this is a simple. This is a simple structure. What we can do. This has been fitted in the schematic. Now check and save is required. Whenever we are pressing a check and save, it will show schematic check completed with no errors. So the schematic has been saved. So this is shown there. Now, as I have told you earlier, that no analog component should be there. Analog library component should be there in the circuit design, because LVS of layout is heavily affected by your ERC, and ERC comes due to your analog component. So we are not putting any analog component. Now what we will do, we will create a symbol. Now we will go to create. Now here in cell view, from cell view we can create like this, symbol will come. Now this I have done earlier to save the time. So now after making OK, this will come like this. So now I am deleting everything and again I am plotting for your convenience. Okay, so this is there. Now I am deleting this one also. Now these are the pins which are coming here. Now just go to create, just shape, you need a line, put a line, put this like this, and some circle is needed, shape, circle, some circle in there. Now you can shift this. Now you can shift everything inside this, and always remember one thing, that this name, in whatever name you are putting as an instance, that name should be same with the file name. This is the important thing which you have to remember. Now we are just putting the nodes, whatever nodes are there. So wire is required. Some wires are required. Now it has been fitted. This is my symbol. Now you have to make a test bench. In that test bench, you can simulate the inverter and see the performance of the inverter. Whenever you are going inside that inverter, it will be showing the circuit, whatever the symbol is there. So for you, I am just making a test bench. File, new, cell view, schematic. I'm just putting in three. Okay, so this is a new schematic kind of thing. This has came. Now I am just calling. How to call? By instance. Press I press. Now in this, what you will be doing? Different type of libraries are there, but our product is in your this library, means T1. So T1, go to T1. Our name is inf2. Just go and press this. So this will be your inf. Okay. So one symbol you have created. If you are going inside this, you can read like this. Means what is inside that thing, you can easily determine. Means inside that this was there. Okay, so what you inside this is there. Whenever you are double clicking this, it will open this one. So whenever you are designing a larger circuit, you are creating a symbols of it, distribute the circuit in small blocks. Symbols will be there, and that symbols you are putting inside a larger circuit. In a larger circuit, only a block kind of things are there, but inside that block symbols, those symbols are there, and then you can create a template of these in a layout also. Then in layout you can directly call them as a symbol, so it will be very essential for you. Yeah, so now now you can just put analog components and you can test. It's not a big issue. So I'm deleting it. So because our topic is layout, so we will be focusing on layout. So these are the primary things. Means what? First, you have to test your circuit, whatever you are simulating. Second, you have to for designing a symbol, you have to remove all the analog components and make them replaced by the pins. And remember that the VDD and the grounds are always input output pins. Now Third, you are designing a symbol. And fourth, you are testing it in the test bench, creating a test bench, calling the symbol and testing the circuit. Now, fifth, what you are doing, now you are going for a layout purpose. Now, whatever you are doing, okay, so create, save, or what you are telling, yes, save it. Now, when you are designing a layout, it will look like this. The layout editor look like this. I think everyone sees this. I will delete this one. Yeah. Now, here I want to just show that this is the layer. Means this is the layer window. Okay. So for your reference, I am scrolling this. As you can see that several type of layers are there. So here GDS number is also there. Here LSW means layer selection window is there. Yeah. So these sets you can determine. Now from here you have the options to remove blocks. We don't need now this block, so I am removing this thing. So now for layer selection windows, before proceeding to that, first I will show what are the options are available in the design. Now ADE means analog design environment. For layout, layout Excel means larger layout, and the GXL, which is incorporating the generic components of the layout. Now layout has different type of versions like L, SE, then XL, then GXL, then Dracula interactive module is there, in which DRC and LVS works. Dracula, inside Dracula. Now different type of cells are there. So in different type of edits are there. Then you can view, redraw, anything you can do. Then create a shape. Then you are verifying your device, circuit in design, layout design by DRC and LVS. Then you can have the probes for connecting like nets and pins. Then you have the option for the display purpose, that whatever the display is there, just like this, if you click here, it will be showing like this. So many options are there. This minor spacing means that the dots, whichever dots, if I am decreasing the minor spacing and the major spacing, like I am putting it as 1.5. So the dots will come inside this. We now see the dots has came. Sir, can you please do one question has come. Hello, just it's blink. I will answer those questions after the presentation. Okay, so now this dots has came. Now what will happen? Now if I press a I, what will happen? Different type of, this is your what? This is your CMOS, which has different types of fingers. How many fingers? You need how many fingers? You have put how many fingers? You have put 30 fingers. Now, if you fit the screen, you can see 30 fingers are there. So this is the basic thing, means whatever you have designed there, the same thing will come here. Okay, So if you are pressing a I, then what will happen? A instance will come like this. Now in instance you are given in your design 30. So the 30 will come. Now you have designed NMOS, but you have given how much? 10. Here you are putting 10. Now it will become a 10 type of structure. Now you can hide this thing. Now you can hide this thing. Now you can put like this. So you can easily see that a symmetric area is there. Now if I want to make a contact, it's a big thing. So just for showing you that whatever you have put in your circuit design, the same thing can be represented in the layout design also. So for just showing, I am giving the fingers and it looks like this. Yeah, so I will directly detach it and I will show for only one finger device. So if it is a one finger device, I will put it one and I will hide this and this will become simple. Okay, so this is NMOS. If we are putting a PMOS, just replace it and hide it. Okay, so PMOS and then your 30 become 1. Hide it. Okay. Can you see now? I think everyone can see. It's a very easy thing. So before proceeding to this, every time remember this type of structure will come. So you have to design in the first coordinate only. Okay, you have to design only in the first coordinate, and in layout you can go in one side or this side. You cannot go triangularly. And one more thing, what you need to know that this whole screen is P substrate. Getting my point? This whole screen is P substrate. So this should be remembered. So we are trying to put these two very near to the this area, first quadrant, because we are always make some kind of error, and the chip size or chip error is always calculated in the first area. So now now we will make symmetry. First we have to make a symmetry. Now what we know that PMOS should be 3 times higher. The width of PMOS should be 3 times higher than the NMOS. So I will delete the PMOS. Again I will go to the I. This is the PMOS. This is should be the 3 times. But what I think that I will not make a finger, because I will directly increase it to the 3 times, like 360. So it will increase it. Now it will make it as a finger. Getting my point? Now if I am putting a number of finger, it is horizontally fingering it. If I am putting that this much area is required, like it is only in the this much area is required, like the area is increasing, so you can see a vertical fingering device is there. So Cadence is so intelligent that it knows that what you want to design. So based on that, they are only making, means if you are putting from your side fingering is there, they will put a layout in a horizontal manner. If you you are putting a finger, you are not putting a finger, you are just putting a total size, it will give a fingers on the vertical direction. So for your to showcase you, I have designed this. Now I can press R or I can create a rectangle. So I will press R and I will zoom it first, and I will make a rectangle. So now this rectangle, why we are creating a rectangle? Because to make a contact between this, but the issue is that this rectangle is of anvil and we don't require anvil now. So this is the layout layer selection window. So which type of layer you want to put, you can directly put, as you know that gate are poly, so I can put a poly. So in metal, you can see it is a newer version of Cadence. Here the metal 11 is also there. So this metal will be utilized for a VDD or a ground contact. Okay. So now we are just putting a poly. Okay. So this poly, whenever I am putting, and now I can see that this poly is very much lower in the size, means the width is very much lower. So we can increase the width by simply editing this. Okay, so I will change it. I can stretch it. Now I just want to show that which layer is which layer. So now you can see here, you cannot edit inside this PMOS because this PMOS is previously done, means this has been done by the contacts. So now the basic theme of creating a layout is, first we will go upside, that we need one layer of a VDD. So I will call a instance. I will shape one R, and I will create one layer. Okay, I have just created one layer. I can stretch it afterwards, not a big issue. Now I will go to the again selection window. Then I will use metal 10. Okay, so the width, see here, if I am seeing the metal, the width is already changed. If I am changing the metal like 6, this will again change. So this is due to the DRC rule check, means they are always remember. Now we'll see, it looks like this. Now if I change this metal to any other metal like metal 4 or metal 6, metal 7, so the design of this will change. Okay, so whenever you are calling anything, it will looks like this, but you have to you don't want to show them that what is the layout. So just you can put a shift, just you can put these things outside it, and whenever you are needed, like this, nothing is there. So whenever you are needed, press F and it will come. Okay, so now what is there? Then we require a contact. We require a contact between your metal lines. So again press R. You need a contact from here to here. Okay, so now this contact should be the same metal, which is the metal of the gate contact. So likewise, I will change this Q, the gate metal. I know that I can put a metal 1 for it. Okay, metal 1 has been put. Similarly, I am again pressing a R, again going downward, and again putting like this. So this will make your, again pressing R, this will be like metal 1. Okay, okay. So now one contact is also needed. So each point, as you know, see here, the points are Q, means the design of that points are Q, white kind of thing. So pressing a, and now you can see these are the contact. White is for contact. So one contact is needed between the metal lines. So these contact you can easily create by the contact filling which is given here. Okay, so here, as here nothing it is given, so we are not utilizing the contact now. Okay, so that has been given here. So this, make it as VDD, so label it. So one label is required. How to give label? Shortcut key is L. If you are pressing a L, it will it comes like this. So label it VDD and just put here. Now the VDD symbol is very big. So go to Q, press Q, and text height, make it 0.1. Text height, and if you are seeing in LVS, yeah, in LVS, this written lines should also be the same, whatever line you are putting. For us, we are putting metal line. So this you have to remember. Okay, is it okay? So if you are changing this to any other lines, it will, like poly, it will look like this, but when you are doing the LVS, they will directly say that your label is not the same as a line. Whatever the line is there, the same line is not available in the labels. So this is a big issue. So this labeling should be the same as the metal lines are there. So this, for your remembrance only, I am putting it. So this type of mistake comes, and I have worked a lot in LVS, so I struggled a lot because for these errors. So we are so now just put some contacts here, some contacts kind of thing. Now how to put a contact? here, just go to Q. Now, this is a metal 1. Now, for metal 1 to metal 7, you cannot go easily. You have to give the via. This is via 1. Okay. Now, again, Q. Again, that R. Press R. Again, the same thing. Now, again, press Q. Again, go to this. Again, go to metal 2. Again, okay. Okay. So, I am putting for our convenience, I am just putting this as a metal. So, Q. This will be metal 2. Okay. This will be metal 1, 2. Okay, so one contact, two contact, and then a contact is needed. So how to put a contact? Again R, again one, Q, go to contact. This is your contact. So this is your contact. So it is not symmetric. Try to create it as symmetric as possible. Here some contact to metal is there. So if you are doing a DRC, then it will show a DRC error because the thickness is not well defined and it is not symmetric. So whenever you are making some contact, so always remember or always go for these type of errors, means these type of errors should be removed. So for that purpose only, these are the guides. So many guides are there that on which kind of symmetry you should put. Here you are putting a guide. Okay, so here you are seeing the routing and the placement. These all these all you can see here, and these are these all are there. So, these are all you can see. Okay, so now different types of objects are there. Not always that you need a triangle type of object. Some circle, some levels should be there. So, so those are required. Then some pins are required. Now I will put a pin kind of thing. Means I will press a P and then it starts like this. How much big contact you want, you can do. Okay, so these are the basic things which are essential. Likewise, I can create lower side also. So I will shift little bit, then fit, because I have to make a ground contact. So it is not symmetric. So I have to create some part of symmetry. So I will press P and I will make a line. So it will create a line. Now I will press Q. I will change the width, whatever width is needed. If I change this width like 5, it will apply, it will increase. If we want to decrease it, it will decrease. Then the layers are there, different layers are there. That, which layer we are using? We are using metal 7. We will simply apply it. We will change it like this. See, the metal 7 layer is there. Now I can change this one also to the metal 7. Metal 7. Not just showing you, I am doing it very quickly. Don't do quickly. Give some time. Okay, so metal 7. So now see, same contact, same thing. So this is required. Again, I am putting some label, put some GND label. Height is equal to earth. Now you can put here. Okay, so now this is the ground. Labeling is done. Now by Q you can change this to metal 7. Now based on this, just apply first and see. It is not consistent. Yeah, it's consistent. So likewise, always remember, delete this. Okay. So again, I want to make a pin. Press P and just drag it to the same point. Okay. Now see, these points are utilized. Okay. They double click and done. It's done. So now I have shifted this. Now by Q, pressing Q, I will change this because we need a symmetric type of structure. Okay, so the symmetric thickness of ground symmetric thickness we can achieve from here. So now what will happen? Again, I can drag it. Now I can see that this has came. It is not symmetry. VDD and ground is this side. So I think label is missing. So we are putting a label VDD. Just here. Okay. So label I put. Now I will change the metal. Now. Now what I tell you that this is not symmetric. As you can see that this transistor is in between, means the lines are like at the edges this transistor has came. So now what I will do, I will simply take this and drag this to make it more symmetric in nature. Getting my point? Now what I can put that thought I have some capacitor or some inductor or some type of resistor. So what I can do, I can always go here, browse this library, and it will always show like this. Okay. So whatever things I need, I can just drag it and utilize it. So suppose P cell is there. So here one layout symbol is also coming. Which type of layout? Metal 1, metal 2, metal 3, metal 4, metal 5, metal 6, metal 7, metal 8, metal 9, any kind of metal 11, because the top level is metal 11. So based on that, P cell level. Why it is P cell? Because as I have told that the window is P substrate. The window of the cadence is P substrate. This is the virtuoso 2 of the cadence. So this is P substrate. So anything you can and now I want to put some inductor. So based on that, this is a P cell inductor. It is a swing inductor. This is a P cell inductor. Now just I will put here. Okay. So this is the inductor. Always remember that inductor size is very large. The chip area, basic chip area is goes whenever you are designing an analog circuit or a power amplifier circuit, some biasing network is required, like some tank circuit is required. So the chip area is consumed by the passive components like inductor, like capacitor. Just for showing you, I am showing one inductor. So where is our device? Our device is so small here. Here is our device. That's it. This is our device. And inductor size is this. Now, now what you can do, that inductor layout is so high that these rotations, basic fundamental of inductor is Q value. So for this reason only, whenever you are designing a power amplifier or any kind of LNA or any kind of amplifier which requires some tank circuit based biasing, you have to go for a larger chip area. So passive component, always remember that passive components take a larger chip area than the active component. So for just showing you that what are the signals, I can tell you that the Q value of this is very low. Why? Because it is not big. The inductors are really big in size. The chip area is very small and the passive components, this is about the inductor. Now I will go for a capacitor. This is a capacitor. It is a P cell capacitor. Now I have put it. So now I will fit it. The capacitor is here. Near the our transistor. So to show you that these kind of mistakes comes. So don't worry about it. Cadence gives you more. Now you can see here it is a MIM cap. What is MIM cap? Metal insulator metal. So how you can create a metal insulator metal cap? The symbolic view of that will be you are just connecting a drain and the source, and you are giving a one node will be your gate and one node will be your drain sorted with source. So these two will become a two type of nodes. For this reason, this is known as MIM kind of structure. Okay. Now so see that if a inductor comes inside the circuit, then it will take a larger area. So capacitor is not taking a larger area, but also in comparison with your transistor, capacitor is taking a larger area. Okay, so now I will show you a resistor. Simple resistor is there. This metal one resistor, simple. This is the metal one resistor. See how big is it? It's simple, a micron resistor. So it's taking a larger area. So always remember. Hello, hello.
Yes, yes.
Okay. I thought something is some issues are there. So see, it is a larger area. So it's kind of halo kind of structure. How you can design a halo structure? Simply remove some part in the substrate and put a metal line. It will create as a halo structure. Yeah, for only for your resistance. It's not the halo structure for your CMOS. So now this is all means this is the passive component, whatever is shown here. Yeah. So now again I come to this circuit. Now I will show that how to put a contact. So now I can keep any kind of things. Okay. So now as you can see, I can put a pin here, pin here. I can put a pin here. If I click here, this will come. Which type of terminal you want to give? You can give like input. Okay, so input will be there. This type is input. Okay, so VDD and grounds are of input output. While we are making your symbol, now it is the input type. Now I can hide this and it will come here. This will act as a pin. Now I can label this pin simple L and I will simply put whatever the label is there input in. Okay, so now I can change the input, so I can hide it. I can put it here. So now I can just change these things. Q, what is this? This is very much high. Okay, we just put it as 5. And then also it is 5. So it is the input. So by Q annual, I will change this to now this is okay. So as you can see, yeah. Now I will just short the pins, yeah, and one body contact I will provide so that every contacts are body contact. So just I will put a body contact by creating a rectangle here. I put a body here. I put a body. Okay, so always remember that in Cadence you have to put a body contact. Okay, so put a body, and body is of which type? For your PMOS, the channel is P, so the body will be annual. So I will create it as an annual. Yeah, it's an annual. So one contact is needed. I will put a contact here by simply putting a R, pressing a R, put a contact. Okay, so just go to Q, change it as contact. Okay, one contact has been created. Now here for NMOS, what is the body? Body will be in the same, the P type. Now I will change it. P, below, that's it. Now I will put a contact here. First R, pressing R, contact. These should be symmetric because I have less time, so I have to just show you that these are like this. So now what is there? That in PMOS the body contact is connected to the source side, and in NMOS the body contact is connected to the source side. In NMOS, source and body both are connected into ground, and in PMOS both are connected to the VDD. So I will just follow the same rule, and I will create a R, and I will create like this. Okay, so I will create like this R. And now what you know that nothing can be done like this. Simply you have to have show, you have to have give some contacts here. So whatever the contacts will be there, you have to go for R, press R, and then you go contact, and after that escape, press Q, make it from anvil. Anvil cannot go like this, so make it like metal 1. Okay, so this will be metal 1, 2, metal 1. Okay, so now more contact is needed here. This contact. Okay, so this here also one contact will be there. Now you have created this contact. Why to for saving the time? You can just copy this for saving the time. Just copy this. Save. Input, input. Only the C means again make a C.
Sir, hello.
Yes sir. Yes sir.
अच्छा,
Yes sir. Yes sir.
क्वेश्चंस वगैरह देखे क्या?
हाँ
क्वेश्चन तो किसी ने पूछा ही नहीं है, तो रहेंगे थोड़ा लो जाइए देखिए.
क्या 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 सर? हेलो.
नहीं, क्वेश्चंस participant you can ask question if is there any you
Yeah
can
yeah
ask
yeah
in the
yeah
chat
yeah.
box.
Okay.
तो सर अभी कितना टाइम और लेंगे आप?
नहीं सर हो गया सर, जस्ट मैं शो किया है.
ओके.
ये तो मतलब बहुत ज्यादा एक्सटेंसिव है कि आपको बहुत ज्यादा ही करना पड़ेगा. खुद से ही करना पड़ेगा. ये तो मैं जस्ट शो कर दिया कि प्रिलिमिनरी कैसे बनता है.
ओके ओके.
ओके सर. सर
Students, if any query you can write in the chat box.
Sir, I cannot see the chat box. Actually, I am utilizing the web one.
अच्छा अच्छा.
Tab is there, so kindly read whatever the questions are there. Some questions were there. Some serious, some question has asked.
नहीं, वो बोल रहे हैं कैन यू गो लिटिल स्लो, बस यही है, मतलब ऑफिशियल क्वेश्चंस तो मुझे दिख नहीं रहे.
Okay, okay, okay.
We'll wait for 5 minutes. If any question is, please ask it. It was disconnected because of some network issue. वो तो आपका पर्सनल इशू हुआ ना, otherwise it is running fine. So you can, I think, stop sharing, sir.
Okay, sir.
अच्छा, where we can download the virtuoso for practice? ये पूछ रहे हैं.
Sir, it is coming from your Cadence tool itself. You cannot download anything. Okay, sir.
Participant, this
From
is a part of a Cadence tool. If you have the Cadence tool in your institute, you can access it. Okay.
yeah. Generally, poly contact is a blue, but in more Cadence. Oh, it is a newer version. For this reason, it is blue. Okay. So chat is coming like this. So little slower presentations. Magic layout. I have given the link to sir. I can copy paste here also the link.
I have
Just
posted it. Yeah.
okay. You have posted, sir. Well, then it's okay. And the detail of magic tool is present.
So I think no more questions now. Then we can stop the meeting, right? Okay. I have
O-
already stopped the recording.
okay, sir. Just I am giving the link to everyone.
Okay.
So
Bharat sir,
it's
are you here? Bharat sir. Bharat sir, are you here? Hello. Hello, Bharat sir.
Just a minute. Uh, Hello.
So you can announce what time the participant can come back after lunch.
Sir, sharp 2 o'clock I will be there because it's only 1 hour class, and
Okay.
later on Rajesh will join at 3 p.m. So,
Okay.
so by 1:45 all the participants are requested to join that
Okay.
meeting
Next
room.
session is 2 p.m. Okay.
Yes, yes.
okay, sir. Thank you, sir.
Shabankar for very informative talking layout design and challenges. So it will be really helpful to the participants. Thank you.
Thank you, sir.